to me, it seems that the consciousness field had to go through that as well. We had to start out with conceptual theories that are metaphorical mostly and intuition-based and intuition-driven. But once we reach this point of being able to develop and employ some formalism, we can leave that behind. And then you gain something that you don't have in metaphor, which is, again, lack of ambiguity, reliability, and precision and rigor. That if you just use words to describe what consciousness is, you just can't get there. Can we really get to a structured description of experience, phenomenology, qualia? And then the second one for people like me that are more interested in the brain would be like, how does this map on the brain? And so then it seems what we end up, and so this is putting it all together then, might be in the end like an equation where we can have on the left-hand side what describes the structure of brain activity, and then on the other hand, the qualia or your phenomenology description, what the visual spaces that you look at right now. What we're really trying to do here is to find these laws, these mathematical laws. And so what Fechner obviously did is not only find that we can measure perception precisely in these thresholds, but also that if you do so, you do find a mathematical law.
This is Brain Inspired, powered by The Transmitter. That is Alexander Maier. I am Paul, almost all the time. Welcome or welcome back. Alex is an associate professor of psychology at Vanderbilt University, where he leads the Maier Lab. His work in neuroscience spans vision, visual perception, and cognition, studying the neurophysiology of cortical columns and other related topics. Today, he is here to discuss where his focus has shifted over the past few years, the neuroscience of consciousness. I should say shifted back, since that was his original love, as you will soon hear about. I've known Alex since my own time at Vanderbilt, where I was a postdoc in Jeffrey Schall's lab, and he was a new faculty member. And I remember being impressed with him then. I was at a talk that he gave. I don't remember whether it was his job talk or soon after joining the faculty. Anyway, it was immediately obvious how passionate and articulate he is about what he does. And I remember he even showed off some of his telescope photography. In particular, I remember a really good picture of the moon. So anyway, we always had fun interactions, even if sometimes it was a quick hello as he was running by me, running up the stairs or down the hallways to get wherever he was going, always in a hurry. Today, we discuss why Alex sees integration information theory as the most viable current prospect for explaining consciousness. And that is mainly because IIT, as it's known, has developed a formalized mathematical account that hopes to do for consciousness what other math has done for physics, namely give us what we know of as laws of nature. So basically, our discussion revolves around everything related to that, like philosophy of science, distinguishing mathematics from the mathematical, some of the tools that he's finding valuable, like category theory, and some of his work measuring the level of consciousness IIT says that a whole soccer team has, not just the individuals that comprise that team. Not only do I link to the work that he's been doing in the show notes in his lab, but I also link to many of the resources and references that he drops along the way to learn more. Those are at braininspired.co/podcast/228. Thanks for being here. Thank you to my Patreon supporters for your continued support. If you do support the podcast on Patreon, you get, for example, all the full-length episodes. For example, in this episode, we go on to discuss a little bit about the free energy principle and how it relates to integrated information theory. So go to braininspired.co to learn how to support this podcast through Patreon, if that sounds interesting to you. And thank you to The Transmitter for your continued support. All right, enjoy Alex. All right, Alex, this has been a long time in the making. I'm really glad that you're here. Let's just start off with, I guess, because I'm interested in also we've talked a little bit about it, but I haven't really learned in depth about kind of how you view your trajectory in. So right now you're like all invested in consciousness science, but you've done a lot of work in visual perception, studying cortical columns. You're a vision neuroscientist if someone called your name, would they attach vision neuroscientist or consciousness scientist at this point?
Yeah, thank you, Paul. Well, first of all, thanks for the introduction. And so it's great to have that. Very many fond memories about the old days, and I've been following you all along. Now, when it comes to my personal trajectory, I should probably start very early on. So when I think back to where did I end up, where now, it started when I had to decide what to study, which subject to pick up for university. And I was at a big loss. I was thinking about law school at some point. I was thinking about medical school. I worked in a hospital for about a year, and I realized, okay, medical school is not what I should do.
Doing what at the hospital?
Yeah, so back when I was young, there was a draft in Germany, and you could conscientiously object. And in that case, you had to do a year of social service. And so what I did is I worked in a hospital, actually in a research lab mostly. It was in cardiology. And so I got to participate in procedures where they used stent implants with people that had heart disease. And then we worked on a gene therapy attempt of trying to prevent that these heart vessels that were getting a little too tight would grow back in. It didn't work, but I learned a lot. And I definitely learned that the medical field is not for me.
Okay, sorry to interrupt. Yeah.
Yeah, and so I then really was a little bit in limbo. The clock was ticking. What do you want to do with your life? And I realized this is going to be a big decision. And I found this book in a bookstore, and it was called What the Soul Really Is. And so that was a unique German title, but it definitely grabbed my attention. And it turned out it was Francis Crick's book, The Astonishing Hypothesis. And so in that book, he lays out the problem of how to explain consciousness from neuroscience. And it's I think, very dated at this point, but it is still intriguing to read that he just basically talks about vision science, and he goes about the neuroscience of vision. And he toys with this idea that we all have of a homunculus, so that when we think about how does vision happen, that is the idea that it all comes somewhere together in the brain, and then that must be where neurons somehow produce consciousness. And so what he does is he talks you through the visual system, and you realize, well, it can't be at the retina. Because, if I close my eyes, I can still imagine a fire truck, and I can see it to some degree. And then he talks about the IGN, and it can't be there, and it can't be in V1. And so you step through the entire visual system until you reach the areas where we know there's activity to faces. And then you realize, well, maybe that's right there then, where we see something. And shows you that, well, if you get a lesion there, you still see a face. You just don't recognize it anymore. So now we left perception or consciousness within the realm of cognition. And so that really struck me, that I had this epiphany that, whoa, there's a big question right there. And in the book, he mentions Nikos Logothetis, who was back then in Germany and doing research on binocular rivalry. That's a visual illusion. If you show two different things to the two eyes, you only see one eye at a time, or one eye's view at a time. And what that allowed the neuroscientists to do back then is to go and find neurons that respond to one or the other pattern and see if they covary in activity with what you see. And that got me. So that wasn't even before I started studying. And so I wanted to then do neurobiology. And so that's what I studied. And towards the end, I approached Nikos and said that I find this work really cool, and if I could do an internship in his lab.
Towards the end of what?
I wasn't even finished with my undergrad degree. So, yeah. And so it was a funny time. He was in a different town in Germany. And so I got all my money together and tried to stay there. And we did experiments, and they worked really well. So it turned out that what we found was then published in Nature Neuroscience. And that, I think, got Nikos interested in maybe keeping me on as a graduate student. And that's what I did. Yeah.
You forced your way in. Yeah,
I forced my way in. Yeah. And but what happened was interesting, that so around this time, that was in the early 2000s, the field had reached a peak of interest in consciousness. And so what I didn't realize was that Francis Crick, with his book, and together with Christoph Koch, a lot of papers that they wrote, people got really interested in consciousness. And what they really meant was perception, mostly visual perception. And that, though, as you probably know, these things in science, that they kind of come and go in waves. So topics get really hot, and then after a while, nobody is really interested because the low-hanging fruit are gone. And so what happened to me is that I stepped in the field right as it became uninteresting. So at least that's what it felt like. So the conferences became smaller and smaller, and so I realized, so what that means is I have to reposition. I have to do something. I can't use that as my research line.
Oh, okay. To survive.
To survive in the industry. And the plan was to, grow old and then maybe find back to it and stay as close as you can.
And you've done just that. Except for the old part. Of course.
Oh, no. That is very much what happened. Yeah. And but I tried to stay close. I tried to keep working on binocular rivalry and related phenomena. But it was a little ironic because what Francis and Christoph and many other people at the time did is they made this topic consciousness scientifically valid. So before that, in psychology, there was a little bit of an apprehension about talking about that. So it was okay to talk about perception, but even that was the odd one out. So most psychology departments, they would have mostly cognitive psychologists at this point, maybe some behaviorist psychologists, and then maybe one or two people that study perception. And it seemed a little weird. They tended to have the papers that everybody was a little apprehensive about because it seems so difficult to take perception and be quantitative and rigorous. And the saving grace that we had was psychophysics, that we could point to, well, you can measure perception quite accurately. I think otherwise this would have been a very difficult topic to study.
Well, I was going to ask you because whether Koch and Crick and Koch include, so one of your heroes is Fechner because of his psychophysics as a window into the mathematics that allow us to form mathematical relationships between perception and perceptual laws, essentially mathematical perceptual laws. Fechner described, but did they point to his work as well? Because correlates of consciousness is not mathematical in that respect. But I wanted to ask you, so were they aware of that, and did they feed off of that as well, or?
So this is a really interesting question that I only thought about recently. And it's partly because of feedback and particular pushback that I get. And so for me, Fechner is interesting exactly for what you said, that it made things more rigorous in the sense that it made things more mathematical. So what he found out is that I can measure very precisely if I make a tone very, very faint and I can't hear it until I can hear it. And so all of us that went to an audiologist have done psychophysics, and that we had tones of different frequencies and we have to tell when we hear the tone. And so for me, that was intriguing. It seemed scientific and rigorous, but I never thought really deeply about what that means in terms of having math in science. I just took it for granted. I think a lot of us do. If we take a physics course or we watch a physics lecture or we take a physics textbooks, we expect there to be equations. But it's kind of actually interesting. Why is that? Why we never tend to think about it? But we also have the psychological reaction that seems very rigorous. It seems very precise. It seems very mathematical. I think deep down we understand that something like Newton's F equals ma or Einstein's E equals mc squared is very rigorous, is very scientific. We have still a leftover vague notion of that's a law of nature and that should be mathematical, should be expressed in mathematics. But even in the physics books, they just take that for granted. There's never a discussion of you pick up this book about particle physics and all you'll find is equations and diagrams. And so over time, I realized that is actually what a lot of this consciousness or perception research struggles with or focuses around with. And that Fechner, that's why you're right, he's my hero, made this very crucial step to show, we can put numbers on perception very precisely by measuring how much do I have to change the stimulus until your perception changes? And then we get numbers. We get these discrete steps of now you hear a difference. Let's call it 1. Let's make the sound even louder. When do you notice it's louder? Well, let's call that loudness 2. And it seems that your perception goes up in these discrete steps, 1, 2, 3, 4, and so on. And I think there's a deep insight, but it hasn't been deeply appreciated or in fact maybe discussed to death at some point in the 60s, where people tried different techniques and showed that, well, under different circumstances, things are kind of different. And so it added a certain notion of vagueness or relativism to that. And so maybe then we lost a little bit that, look, what we're really trying to do here is to find these laws, these mathematical laws. And so what Fechner obviously did is not only find that we can measure perception precisely in these thresholds, but also that if you do so, you do find a mathematical law. So he found that our perception tends to be logarithmic. And that's a big insight. So it actually is, for example, when it comes to how we make purchasing decisions, a big impact on us. That if we buy a very expensive car and they add another $100 fee, we accept that because we already paid $10,000 or $20,000. So $100 doesn't seem much. And so people are toying with this fact that we have this logarithmic squished kind of perception where in the very large things, everything seems to be a little closer together. But to see that as a law of nature goes a little far, maybe. But that, to me, seems to be the goal of science. It seems that we debate a lot in science until we reach that stage. So what I mean by that is that Darwinian evolution, for example, still gets a lot of debated. And I think it's because, well, one reason for that is that it's not as formalized as E equals
Right.
MC squared is. I think there's just less debate about that once you write this down and you show it works. And so that got me thinking a lot about how the goal of consciousness science, as you said, should also be mathematical. It should be to find these fundamental mathematical equations or other kind of mathematical structures or objects that give you the same kind of rigor, precision, and unambiguity that you find in physics.
So did you appreciate that? Did you come to that realization before knowing about integrated information theory, which is a lot of what you work on now, or what? So we're going to talk a little bit about integrated information theory, but part of what I wanted to ask you is whether it's IIT itself or the fact that it uses formalized mathematics that really draws you in, like which of those are you really interested in, or both? But my original question here, and we'll get into that, was, I mean, is this like like an epiphany that you had one day about mathematics, that this is the way?
Exactly. This is what happened. So my way into IIT, ironically, is over the evidence. So there's now a lot of debate where some people are criticizing that it is difficult to, what they would say is falsify IIT or test IIT. And so my, again, autobiographical history has been that back when I was working on consciousness quite intensively, I got to encounter integrated information theory in its infant stage. So those IIT 0 or IIT 1 or IIT 1.5. And so back then, it seemed not very useful to me as an experimentalist. It was kind of unclear, what can I do with fMRI or my electrodes and so on. And but then what happened was, and I remember this very distinctly, a science paper come out, a paper in Science, where the prediction was derived from IIT. And the prediction was that if you're unconscious and you stimulate the brain with an electromagnetic pulse, with TMS, and you measure the EEG response, it should be very different. And the prediction was more precise. The prediction said that you should see no more integration because you're not conscious. And the way that it should look like is that you get local excitation and it shouldn't really cause some kind of complicated pattern. And the interesting thing was that has never been tested before. That has just never been done before. And the theory gave this prediction. And so because I had this personal history, I knew this was a genuine prediction, which often in neuroscience, at least around this time, was rare. So it tended to be that we were in a data-heavy collection period. And often to publish your papers, you would collect the data, try to make sense of it, and then add a theory post-hoc. Here's my model of what you did.
We still do that, of course. Well, that's also, exploratory science, right? But so there's a place for that. But
it doesn't seem what physics does, right? So we all understand it's more powerful to make a prediction and test it than to fit a model to your data, because I think it was von Neumann who said, give me 3 variables and I can fit you anything. And so it was definitely interesting that here it seemed to generally happen. And it was a theory of consciousness, no less, that made a prediction, and that's what they found. In fact, they've gone on and throughout the next couple of years, then they tested different anesthetics, and they made an exception, for example, for ketamine, where we know that people are not they seem unconscious, but actually they hallucinate. They're in a dreamlike state. And lo and behold, you get more a consciousness-like pattern under those circumstances. In fact, this technique is so powerful that now there's video clips. If you follow Marcello Massimini, who's been leading a lot of that, a neurologist in Italy, they had now patients that were misdiagnosed as being comatose. They use this technique, they find out they're conscious, and then they can treat them, and it turns out, yes, they were conscious all along, but they couldn't respond, and so therefore they seemed
locked in patients?
It's actually the one case, and I hope I don't get it wrong, but like one case, if I understood correctly, was kind of interesting. It was a lack of dopamine. And so that is, if you watch the movie after Oliver Sacks' book, that after the Spanish flu, Awakenings, yeah. So after the Spanish flu, that a lot of these people became catatonic, and he gave them L-Dopa, I believe. And so they produced more dopamine. They came back. They could behave. And they said, I was conscious all along. I just didn't feel like responding. And so this was a similar case. I think that patient seemed unresponsive. And so the physicians didn't know whether it's coma or not. And then they gave L-Dopa, from what I understand, and the patient became responsive. So I'm born, and so I know that there's a whole company that now wants to make this a neurological project. I'm just saying this seems to work. There's a lot of evidence that it seems to work, and for me, it's quite compelling that it really came out of this theory making a prediction. So that gave me a lot of interest in IIT. And so the next thing that happened was that IIT evolved. So now we're in IIT 4. And what happened in particular is that it got more and more fleshed out mathematically. It's not actually really every time a new theory. If you read the very original papers by Giulio Tononi in the early stages of IIT, you see it's all there. It's actually really interesting to follow
the axioms have not changed. What's changed? What changes for every iteration then if it's not what's new about it?
The axioms have changed. And it wasn't it wasn't as axiomatic in the beginning. It was a little bit less formal. And so, but you see the ideas are there. And so what has happened over time is that the formalism got worked out. And so then the next paper that really grabbed my attention was by Angus Leung and Nao Tsuchiya. And so what they did is they used IIT 3 back then, which was the first really complete mathematical apparatus that you could implement in MATLAB or Python. And they would use it on local field potentials, so just voltages, e.g. like signals from fruit flies, Drosophila. And they had two kinds of recordings. It wasn't with these multi-contact electrodes that we have now in the fruit fly and the mushroom body, which is the brain-like structure. And they put them either under general gas anesthesia or not. And so it turns out that the insects, they have sleep-like states, and they also respond to certain anesthetics that we have as we do. They stop moving, and they seem to be unconscious. Now, that's a stretch a little bit, but this certainly mimics the behavior that humans have under these conditions. And what they showed is that IIT, to some effect, works again. So the prediction of IIT would have been that you find a lower phi value, which is what we can now compute. And that's exactly what they find that happens during the anesthesia if you make a lot of assumptions and cut a lot of corners, of course, with the actual data. But it worked.
Sorry, let me just interject. As you just dropped phi, and I just want to make sure that everyone knows that phi is the end scalar value of the amount, quantity, level of consciousness of a system. And we'll get into maybe we'll get into some of the issues surrounding the calculation of phi and what it means. It's actually, we will get into it because I want to ask you about it. But when Alex says phi, that's the end result of all the math that goes into IIT.
Right. And
Sorry
so what
to interrupt. No.
Julia, thank you for doing that. So what Giulio Tononi's lab did is they wrote Python code that anybody can use. It's public, it's open source, to compute phi values from, say, neural data. So it is quite feasible to do so. Now, there's, of course, a lot of debate about what does this mean, phi, and what does it mean to have a scalar for consciousness. And this is where I come back to what your original question was, that after I realized all of that, look, there seems to be something there. There is evidence there. And so my view about science is not falsificationism, but believe in people like Nakatosh and Quine that have pointed out that there's issue with that. I have a more of a Bayesian kind of view in terms of you just accumulate evidence and then you weigh what is more likely than something else. And so there seemed to be an increased likelihood of there being something there. So that's when I then started toying with that algorithm myself and with the mathematics myself. And as you said, that is what led me directly into thinking more about what are we doing? And so why is it working? And what is this thing, mathematics? And how does this relate to science and nature? And so that's what led me a little bit this philosophical rabbit hole down in terms of thinking, is IIT interesting because it has this mathematics which most theories of consciousness do not have or not to the same degree?
Is just as an aside, I mean, do you... I know you're not going to say negative things about other avenues of research regarding consciousness, the nature of consciousness, but what I really want to ask you is, do you see other non-mathematical approaches to studying consciousness throughout history and present day? Is it a waste of time? Is it just a category error down the wrong path? It's never going to produce a satisfactory explanation or law that we will be satisfied with scientifically. How do you view that without getting yourself in trouble, perhaps?
Yeah, no, thank you for the questions. I actually I've thought a lot about that recently. So, and it was because I got in touch with linguists, and they convinced me that in the field of embodied cognition, there's an interesting subfield of embodied linguistics, if you want. And what they said has really got me thinking is that fundamentally, when we throw around concepts, in particular in science, what we do is we kind of think visually, all of us. It's all metaphor-based. And so that was a big pill to swallow for me. But I struggled to come up with, think about physics, about anything where I don't just have a little bit of a movie or a graphic in my head. So if I think about space-time, I see all of these things where it's actually a two-dimensional surface that's folding and a ball is rolling. And I can't fully envision it otherwise. And so that's clearly just a metaphor. But you can get stuck in this metaphor. And you can think, I understand what space-time is intuitively. And so I refer to that. And then if you talk to other people that watch the same videos or animations, they will think very like you. And I think the interesting thing is, of course, that's flawed. And so, but that seems to be what science might always be doing as a first step. And so once I had this in my head, now that I go to any scientific talk or watch a YouTube talk, I realize, well, this is actually what happens a lot. Especially if people talk about cutting edge findings, often they deliberately will say, oh, it's like, let's say it happened recently. Somebody talked about sleep and what happens during sleep. And somebody said, oh, it's like the cleanup crew comes in and cleans up after the party happened. Sure. And I realized, that is what we'll have to do. We have to use these metaphors initially. We kind of get what somebody's talking about because we do not fully understand the molecular mechanisms here. And
well, so they're necessary and they're useful, but they're also inherently limited,
exactly.
like all models. Right?
Exactly. And so if you look into, I got really interested in the history of physics, in finding out why math. And David Kaiser has a great YouTube series on physics in the last century on YouTube that was published during the pandemic. It's an excellent watch. And so a lot of dots connected for me. So the interesting thing, for example, about Einstein is that he really started out with metaphors. He would be very deliberate in using these thought experiments. And you might think that, well, maybe people didn't appreciate that much. But then I found out that when it comes to Heisenberg and Bohr, to some degree, that was the case there as well, especially Bohr. They would often actually argue the famous Copenhagen debate. They would often argue in metaphor more than in mathematics. And what happened with Einstein, a lot of people know, is that in special relativity, somebody had to come in and show what the Lorentz transformation actually is in terms of formalism. And then in general relativity, that there was also, it was very important to work out the tensors and the mechanics behind it. And it's interesting history in Heisenberg's case about quantum physics that he seemed to kind of reinvent linear algebra in terms of only trying to describe things formally. So it seems that the formalism was next. So metaphor first, formalism next. But then the formalism opened a new world. It's thanks to the formalism that we can even get a grasp at quantum physics or relativity, and then probe extensions and do precise measurements and have precise numerical predictions. And so I think that, to me, it seems that the consciousness field had to go through that as well. We had to start out with conceptual theories that are metaphorical mostly and intuition-based and intuition-driven. But once we reach this point of being able to develop and employ some formalism, we can leave that behind. And then you gain something that you don't have in metaphor, which is, again, lack of ambiguity, reliability, and precision and rigor. That if you just use words to describe what consciousness is, you just can't get there.
I mean, we have to use words because we're limited beings, but what if so it begins with intuition, which you translate into a metaphor to communicate the idea, and sort of, it's like you're chiseling away at something, right? And maybe if you do it really well, you end up with a formalized mathematics that can test the predictions. What if your intuitions are wrong? What if the original metaphor is wrong? I mean, I suppose that are there examples? I don't want to go down this road. I was going to ask if there are examples where the metaphor, to begin with, ended up developing a formalized mathematics that made good predictions, but ended up being the wrong way forward.
The first thing where my mind goes to is what your work has been on this podcast, that a dominating metaphor in the cognitive sciences is computationalism. And there's some formalism coming out of that. But you had several people on there pointing out that that's just a metaphor and that there are limits, and that taking the metaphor for the map for the landscape is maybe something that a lot of us are realizing at the same time has stifled progress. And so but
it's interesting. Sorry, I'm sorry to interrupt, but it's interesting that fact that Alfred North Whitehead called it the fallacy of misplaced concreteness, mistaking the map for the territory. That's actually more widespread than ever right now in computational neuroscience. So yes, a lot of people are aware of it and realizing it, but as computational models have come to dominate the landscape, people are mistaking the map for the landscape more and more, especially in the artificial intelligence world where a lot of people think that computers are conscious and, all of that. So anyway, it's interesting that, yes, people, it's almost, I don't know if you have to go through that computationalistic perspective to then get beyond it or what, but it's really more widespread than I would imagine it would be. But there you go.
I see it a little bit the other way around. But obviously, go ahead.
That's because of the silo that you're in these days, I think.
It could be.
I'm in a silo too, but yeah.
It could be.
So anyway, yeah.
It could be, but I see the silos cracking a little bit. So what I find interesting is that I got obsessed with this a little bit because a lot of the pushback on IIT comes from a computationalist perspective. And so I realized that we have to go all the way back down to the foundations of the house to actually come to an agreement. And we already disagree on, for example, the philosophy of science. We also, disagree on basic things like what's the role of computation. And so I looked into the history of computationalism. And so what I find interesting there is that, here's my interpretation. I think that psychology always struggled a little bit as a science, as seen as a rigorous science. And so often the psychology departments are a little bit placed in between the humanities and STEM. So it's often the deans don't quite know where to place it. And I think psychology, now you might say, well, we started with Helmholtz, and wasn't that exact science? Wasn't he an experimentalist and a generalist? But you see in William James, who's maybe the founder of American psychology, that there was a very strong emphasis on philosophy. And so, yes, there's almost more of a humanistic streak. And I would argue that Freud was then the problem. So as a lot of people know, he wanted to become a neuroscientist. He was supposed to, if I remember correctly, as a graduate student, come up with something like a Golgi stain or a Nissl stain, and he failed. He tried to have silver stain for neurons. And it seems almost like he started to hate this all so much that he just flipped the table and made everything literature. And so that is where falsificationism comes from. So Popper is trying to react to that and is trying to say, that's not science. And then when people say, well, why is psychoanalysis not science? He's like, well, it can't be falsified, right? So this is where this all comes from. That's why physicists never hear about falsificationism. And in the psychology and then the data science, cognitive neuroscience, it's so prevalent. It goes back to that debate. And it also triggered behaviorism. So what seemed then to be the saving grace in the 1930s was to say, okay, we're just going to cut everything out that can't be observed directly. And that goes back to Ernst Mach. It helped in quantum physics to say, let's stick to the observable. And that is still a dominating streak that, though, made psychology difficult. If you look at some definitions of big psychological organizations, they still have in their definition that it is about the behavior of humans, as if it wouldn't be about love and seeing the color red as red and blue as blue and so on. And so that goes back to this historical thread. And I think what computationalism did in the form of the cognitive revolution, as they call it in the 60s, and I think this is not pretty doubtable, is that computers became the saving grace because you could point to a computer and you could say, look, it's got memory. I can't really observe it. All that I see is silicon and transistors flipping on and off, but it is the behavior, if you will, of memory. So I can study this in humans as well. And you can't accuse me of pseudoscience. You can't accuse me of grasping at straws, of something that is immeasurable fundamentally or abstract, non-existent, just a concept.
And it's a function.
Exactly.
It's replete with functions. Yeah.
Exactly. So at that point, you get wedded to action and functions. And so that, I think, goes back even further to, if you look at the history of physics, how prevalent the mechanistic worldview was. So people sometimes confuse this with materialism, but this whole idea that fundamentally you have the world made out of atoms, or atoms are made out of even smaller things like neutrons and electrons, and maybe they're made out of quarks, but that's just smaller and smaller ping pong balls, tiny little bundles of mass. And when we talk about force, what really happens is they move and then they bounce. And so this is what James Ladyman calls micro-bangings, that the whole world is just made out of particles that bounce around. And that gives this idea of mechanism, that everything is about motion, which of course was the starting point about physics, and in Newton's case has proven so successful that, yes, we can explain a whole lot with motion. And that physics in a way is it's the science of change, it's the science of motion. And so that all trickles in there, that I'm so focused on process, on change, on function, on transition. And so that is what comes baked in the cake with computationalism, and where I think then some friction arises with consciousness.
Yeah. So, okay. Well, so we started this little aside by me saying, has there ever been an example where intuitions have led astray? And so we started talking about computationalism. But before that, we were talking about how you were saying that sure, you can begin with metaphor as all things do, but as soon as you get a mathematical formalization, then you can drop the metaphors and move forward. And that's what the strength is of mathematics in your view.
In particular, I think it's formalism. So let me give you an example. We recently worked on this crazy new project where we opened up a review paper that we wrote about predictive coding. And we said anybody who's interested can participate, and we're going to write a literature review that really looks at everything that has been published on that, summarizes it. And the goal was to come up with open questions and find experiments that could be done to solve them. And what was interesting to me is that at some point in this process, it seemed to me and some other people that we weren't really on the same page linguistically or semantically. So people would use terms rather loosely in terms of expectation or prediction. And so to me, as somebody who read Francis Crick, I was always a little bit scared of the homunculus problem, where you invoke there's a little mini me inside your head, and that's expecting, and that's I tried to find out what do we mean by that. And so the suggestion became to write a glossary. So we take each of these words and we defined them. And that became a really interesting experience because while this paper is more than 100 pages and 60-something authors, and it worked, and it was quite the experience. And I think the result is something else. But most of the time was spent, on my perspective, on the glossary. I think if we would count the edits and the effort that went into it, there were whole wars fought over simple words like prediction.
How to define them.
Yes. Now, the interesting thing that I learned is at the end, I was quite happy. I thought, okay, so finally we have a glossary for predictive coding where we don't just use a word like internal model, but we define what it is and how it relates to predictions and prediction errors and so on.
But still in words, not in math.
Exactly. So then I learned about, I got interested in category theory, and that's a whole different topic. But so integrated information theory has now been a little bit married with another approach by my friend Naoto Tsuchiya, where he's expanding psychophysics as well, using structural approaches, and so taking the structural nature of IT and making it, putting it in a bigger diagram. I don't want to talk too much about it now, but I got interested in this topic of category theory, where category theory, in some ways, I will get bashed by the mathematicians, but an easy way to think about it is that it's very graph-based. So you have arrows between things. And so these could be functions. They're more generally called morphisms, like some kind of relation. Things are in relation to each other. So you get something like a graph with arrows. And so there's a lot of interest right now, from what I understand, in mathematics in category theory, because one reason is that it seems that you can base all of mathematics on category theory. It's a foundational theory. And so it's a rival to set theory, which we've done over the last 100 years or so to base all of mathematics on that. There's some other reasons why it's interesting. It's very interesting in computer science. There's several programming languages that are based off it. And so there's a lot of research going on. And so I saw this talk by David Spivak, who is leading a whole institute where they're working on category theory and how can it be used, with John Baez and other people, how can it be used for people like you and me? And they came up with a software. It's called an O-log. So it's an ontological log, and where ontological is not the philosophical term here, but the computer science term. So the idea is that if you build a logic or some kind of system, you should be very precise and semi-formal. And the way it works is that you can take your theory and then you can cut it into what we did, for example, a glossary, where you have these terms, and now you're a little bit boxed in, ironically, by set theory. So a good O-log would use every term that you have, put a box around it, and make it an element of a set. And what you then do is you connect it with arrows, how it relates to all of your other terms. And so if you really want to be very rigorous, the way it works best, if these arrows, the relation is just a verb like is or describes. So what you get is a graph, a kind of a network that shows your whole theory, and you can read it. And so there's good examples on Wikipedia where you can take scientific concepts and you can make them semi-formal, semi-rigorous. It's very graphical as language.
Semi-rigorous. Okay. Yeah.
Well, it's not numerical, right? It doesn't give you real numbers or natural numbers as an output, but it's structural. It limits it because it has formalism. It limits. It doesn't give you the ambiguity that language does. Where if I have a sentence like, I didn't say you stole my car, I could say, I didn't say you stole my car. I didn't say you stole my car. I didn't say you stole my car. So you don't have this problem that language has, that there's
no interpretation problem. Yeah. Okay.
Exactly. And so I started doing this for this glossary. So I put in these words that we defined, and I put these relations in between. And in doing so, I realized that there was one concept that had no connection to anything else. So it was in the glossary. It's a key term, but it had no. So for these relations, I used the sentences we wrote, such as is or describes or predicts, and so on. One thing I should also say, there's one more step I forgot. As you define a word, let's say prediction error, to make this OLOG really work, you use type theory, which is an extension of logic that started with Russell finding out that there's problems like paradoxes in set theory, and they can be resolved in type theory. And it's a very simple trick. Whenever you define something, an element of a set, you have to say which set it belongs to. So, for example, when I say prediction error, I have to say what it is. And so you do colon and you say what it is. So prediction error, and I would say a signal, right? And so then I could define what a signal is. But there were other signals in there and so on. So everything is typed, and then you have these relations. And so I found this one thing that was typed, but it had no relation to anything else. And so that is where I realized we made a mistake. So that's like literally a distinction without a difference. So there's now a part of the model that you could also just cut out. But
what is it? Does it matter what it is?
I think it might have been internal model, but there was one concept that is quite key for the theory, but it wasn't linked in our definitions. And so the epiphany that I had is like this little bit of what I call mathematics, a little bit of formalism allowed us to see that, look, we actually got duped by our language. Nobody detected that this glossary was flawed, that there's a term in there that has no relations to any of the other terms. But then we happily use it throughout the review. So this is where I see that formalism and notation in particular can be very helpful in science.
Okay, so let's. You said you didn't want to talk about these things. I'm going to read a quote from one of the review that you wrote with Now about qualia and using the integrated information approach and mathematical formalized approaches and structuralism. Structuralists believe that it is structural relationships that determine qualia. Is it a good time now to unpack that? I fear, because we could talk forever about the background, the philosophy, and the usefulness and stuff. So, but I kind of want to get the gist of where your head is and what you think is important in terms of studying consciousness and within the formalized mathematical sense. So, what the heck is structuralism? Why is it important? And I don't know if you want to say what qualia is, because in the paper you guys use it to sort of encompass all of what we consider subjective experience, consciousness. It's a substitute term for those sorts of things. The feeling of what it is like is qualia, etc. But given that quote, structuralists believe that it is structural relationships that determine qualia. So what is structuralism? Why is it important in a formalized mathematical account, etc.?
Yeah, thank you. Yeah, it's a big topic, as you said. So, but the main simple idea is that your experience, your consciousness, and so again, I equate it with experience, is non-arbitrary. That is how I can put it the most simple. So there's an order to things. And so the easiest way to understand structure is that there's a pattern or an order or a lawfulness behind everything. So, and that goes pretty far. So for example, as you sit right here, you cannot see what's behind your back. So you experience visually what's in front of you, but it clearly has a limit, left and right, where it just drops off. And so you can't see 360 degrees around you. And of course, there's more, which is that you see color in front of you, but it's not jumping around, moving around, unless something's actually moving. So stationary objects, if you have a red object in front of you, it just stays put right there, and it's exactly in this position. And you can go even deeper and think about, what do I mean by position? And so that is where structure comes in, where you would say it's actually a relation. It's that this thing is to the left of that, up from that, down from that, and so on. And then you could say, well, that's a certain distance. That's another relation. You can say, well, it's 4 thumbs, that it's up from this and 4 from that, and so on. So the fundamental insight here is that consciousness, even though it seems so ineffable for a lot of people, I can't describe you what love feels like, that actually might cut short. And so there are things that we can find out about consciousness, in particular the structural relations. That goes further. It becomes easiest to understand for a lot of people if you think about different experiences. So now I talked within an experience. I'm saying that if you open your eyes, what you see in front of you is structured. It has order to it. It's not random noise. But between conscious experiences, it becomes even more clear. So if I say the color red and the color orange, how do they relate to each other? Then orange and red to green, you would say that orange and red, they're more similar. They're closer together somehow. They have a closer relation than the color green. And so obviously this is how we construct a color space. We can measure these distances, then we can place these colors further apart if we say they're less similar, and closer together if they're more similar. And then lo and behold, we get geometry, we get a structure, we get mathematics out of that. Now, it's not the algebraic numerical mathematics that we usually use necessarily, but it shows you that there is an order that we can discover. And obviously that is exciting to a scientist, what we talked early on, that Fechner tried to put numbers on perception by saying each time you cross a threshold, I can go one up. So you have 1 pane, 2 pane, 3 pane, and it seems to jump discretely as I make things more painful. But now we're getting to a more rich concept where I'm saying, well, I can actually describe, for example, color in a 3-dimensional space. And so it's a 3-dimensional object that I can now use regular geometry to describe. And so it seems that we're getting more rigorous, more formal on something that seems to be as ineffable and loose as consciousness.
Oh, you guys used the phrase enriched psychophysics in that paper to describe this, enriched structures, right? And I'd forgotten, you discuss in your talks, I don't know if you do in the paper, but yeah, I think you do, that Fechner sort of realized, okay, well, this is an outer psychophysics, quote unquote, outer psychophysics that I'm doing, and knew that eventually we would need an inner psychophysics to describe how the brain relates to consciousness, et cetera. And so you guys are proposing that we need a new enriched psychophysics, I assume pointed on the inner side, to describe these like color spaces and these higher dimensional kinds of structures that then should isomorphically map onto our qualia.
Exactly.
It's a mouthful. Is that right? Okay.
But you got it. It really is just a couple of years ago that it fully hit me. And I think IIT should get credit where credit is due, because I think this basic idea that if we have a geometrical description of your conscious experience, and let's put aside whether that is all. I think there's a lot of debate whether, well, if you describe all the geometric relations in my vision and so on, there still seems to be something about the redness of red that this can't capture. And I want to put this aside. I think IIT does this too. It's just saying, well, let's just go this far, that we say that I can describe what you see geometrically, and I can describe music geometrically. And for example, that if I go up in tones, they go up. But then if I hit an octave, I get a closer similarity relationship. So it seems to become like a helix where tones of the same octave are underneath each other, even though they spiral up. And there's other examples like phase spaces and so on, where if we order things by similarity, I get a geometrical structure. And I think what IIT does, which I think is brilliant, and which now Tsuchiya is expanding even more, is to say that if we just put numbers on perception, it kind of gets unclear what we want to look for in the brain. And so maybe that is also why this project of the 90s to some degree stopped, or never really fully embraced psychophysics. But what we should be finding is that there should be something about the structure of the brain mechanisms, and I'm using this term deliberately, and I can explain in a moment, that should be isomorphic or in some relation, in some other structural relation to this thing. Because how else could it be that my vision is ordered if whatever, and I'm going to use this term very carefully, if whatever supports, some people would say represents that visual perception, is
supports.
unordered.
Yeah, that's way, yeah.
This order has to map onto some kind of order in my brain, right? So that's a basic idea. And so this now seems to be an entirely different research project, that if we can, and so I think these are two separate projects. The one big project, people like Johannes Klein are quite interested in, to some degree, a lot of work that that now Tsuchiya does. Can we really get to a structured description of experience, phenomenology, qualia? And then the second one, for people like me that are more interested in the brain, would be like, how does this map on the brain? How can we use this to map on the brain? And so then it seems what we end up, and so this is putting it all together then, might be in the end like an equation, where we can have on the left-hand side what describes the structure of brain activity. And as you know, there's been a lot of work on this recently with topological data analysis, higher order beta latent spaces, manifolds. These are just structures, information structures, people would call it. And then on the other hand, the qualia or your phenomenology description, what the visual spaces that you look at right now. And that relation in between could be an equal sign, it could be an isomorphism, it could be an adjunction, which is an even weaker relation. But the idea is, roughly speaking, these are two graphs, and I can transform one graph into another graph. The interesting thing for me is that it seems to me that at that point it's E equals mc squared. It seems that at that point, and I think that's why some people say it would solve this, what people call the hard problem of consciousness, that you can't do it. You can't explain what love is based on your brain activity. It just doesn't seem to work. And to me, the answer seems to be, and obviously this is a pipe dream, this is vision, this is intuition now, that I'm saying, no, once we reach this point that we have an equation where I can put in the brain activity on the left side, on the right-hand side, I get the description of a mental state, that seems to be a law of nature. And so if this is a general universal relationship, that we found something like E equals mc squared, and if you still squabble with that, if you still say, doesn't satisfy me, you have that same problem in physics. And people do, by the way. So if you describe the whole world with quantum field theory, which is very potent, is the best theory we have in terms of precision, gives you 13 decimal points of prediction that people then at the particle accelerators in Switzerland and elsewhere find. That's as precise as it can be. And yet, it's just math, right? In a way, it's just very complicated Excel sheets that predict what you should find. And so you get the same problem that some people say, well, at that point, I'm unsatisfied. It seems that there's more to the world than just this math. And I think there's two ways to go from there. One is to say, well, but that's all that you get epistemically. All you can know, all that science gives you is the math, is the structure. And then if you want more, that's fine. But then it's outside of science. Like science can only give you the math. Yeah. And so science, now for me, it's interesting to say, well, why would you assume there's more? I would push back and say that I'm quite satisfied with the state of the world to say that, well, maybe fundamentally it's all relation. And so, but I understand why some people would object. But so let me say this real quick. I think that when we talk about mathematics, we use one word for two different things. And so this one thing I learned from Peter Fried, who on YouTube has a great lecture. It's called An Anti-Philosophy of Mathematics. And so what he says is that what people think of mathematics is that it's a language. It's just a superior language to what we usually do. And so there's a lot of evidence against that. And in particular, neuroscientific evidence. So Stanley N has done neuroimaging studies where you have people do and learn math or read math and language, and it's different parts of the brain, right? So that is already a problem, that your brain doesn't think it's a language. It doesn't treat it as a natural language. But I do agree that there seems to be something man-made about mathematics. And so this is, I think, where a lot of people get hung up and think, so look, if it's us in the armchair that are doing that, it can't be nature. So there's a tension that you see in Newton already. Like, why is it F equals ma? Like, how does this go with a mechanistic worldview? Like, what is that law of nature?
Right.
How's it coming from? I can't see it. I can't point to it. And so, yes. So when it comes to notation, when it comes to proving things, when it comes to thinking about math, writing out math, that seems subjective. It seems to be mind dependent. It doesn't seem to be something mind independent. But what I think somebody who has that view has to admit there's something mind independent about this, right? And so Peter Fried would that call the mathematical. And so what that means are, what are these rules? Where do they come from? So yes, if I write down 2 plus 3 is the same as 3 plus 2, that's me. These numerals, Hindu-Arabic, we agreed on a plus sign even later, and so that's all man-made. But there's something deeper in there, which is that if I say 2 plus 3 is the same as 3 plus 2, what I actually do there is I say I can switch things around. It seems trivial, but if I take a book or a piece of paper, let me grab one real quick, and I try to do the same thing, and I say let's go forward and then to the side. I have it this orientation, but if I say go to the side and then forward, I end up in a different orientation, right? So there it seems that it matters very much what the order of operation is. And so this seems trivial, but I think this is where a lot of scientific insight is gained, but to thinking like children again and asking these trivial things that we take for granted, why are they this way? And so Peter Fried would call that the mathematical. Some things commute, some things don't commute. So that would be the fancy word for that. It matters whether you move things around or not. And that seems to be mind independent. It seems more like we discover that. And so there's evidence, for example, that we found the square root of -1, I, and it seemed just a ludicrous idea. It's like, okay, you can do that if you want in your formalism, but in the real world, it doesn't matter. Like, there can't be that, right? And yet, there's a lot of debate right now, including Nature papers, that it seems that quantum physics, the formalism, collapses if you don't use complex numbers. So you need that weird thing that we thought is us, is our brains, humans made that you can take the square root of a negative number. And yet nature tells us, yeah, you can have a laser pointer without that. So right. I think that points very heavily to that while mathematics is a human activity, it points to, and if you wanted to call it a language, fine, but it points to or describes something that seems to be mind independent. On that view, it would be structure. So a lot of people that delve down to that level, they would say, yes, fundamentally, that's all structure.
One is tempted okay, so when you describe things mathematically, right? So you have this relation of how things progress through time. F equals ma, E equals mc squared. These relations, right? And some, maybe I won't say mathematics. I'll say the mathematical. One is tempted then to say, well, maybe the mathematical is actually what's real, since it seems to be what we discover. Yes, it's a product of our minds. We can't apprehend the mathematical without our minds, but every time we look, it's almost a discovery, not like a produced language, right? And there's this like slippery slope. Do we discover it? Did we invent it, et cetera? But that's almost an idealism perspective on metaphysics, right? So does the mathematical, does it lend itself to an idealism in metaphysics, or how do you think about the mathematical?
Yeah, this is now very deep. So the word that I often think about is neo-Pythagorean. So Pythagoras said is all is number. And so he thought about this. This is the word just made out of math. Now, Max Tegmark has this famous book. His paper is even better, Our Mathematical Universe, where he makes a similar point. And so a lot of people would say it's Platonic. So the mathematicians that believe that numbers are real, they're Platonists. But it's actually not Platonic, because Plato would say there's a real world and then there's the abstract world, right? And so this is basically saying, no, all is relation. And so what really got me thinking in this way were a lot of discussions with Naoto here, who also showed me that the Buddhist perspective goes this way. And then work by Tidane Bradley, who's a mathematician, a young mathematician. I think she's the head of Google AI at this point. And she took a summer school where she learned about category theory, and she has this beautiful handwritten diagrams and so on, and she made it all publicly available. And so she introduced the Yoneda Lemma to me. And I remember when Naoto wrote a paper on the Yoneda Lemma, I thought he had lost it. Back then, I didn't think about mathematics. I was really, I felt sad. Because you probably agree with that mathematics can be used as a ruse in science.
Yeah. Well, yes, of course. Everything can, it turns out.
And so I think that I heard a song once that said, if your results are dubious, shroud them in higher order calculus. And so
that's right. Yeah.
There is something too. And I had it too. I was very bad at mathematics, I should say, by the way. My love affair with mathematics is fresh.
Why were you sad? You were saying what were you sad about?
Yeah, so I thought this is it. This is basically, so you might know about the Sokal affair, right? So that continental philosophy seemed to be in this decline in terms of logical coherence and so on. And then physicists published papers using math, making supposed philosophy, and it was all demonstrable bunk. There's a whole discipline out of that now that I highly recommend anybody look into. It's called bullshit studies, where they deliberately produce computer-produced bullshit. And about 40% of people, they do not just recognize that these are illogical bullshit.
Is this different than Harry Frankfurt's concept of bullshit? Like philosophical concept of...
Yes.
It's the same?
It's different.
His is not deliberate. Okay, it's different. Yeah.
It's different. This is actually, it's embarrassingly enough, not made by psychologists, but by economists. So they have these random word generators, and they generate these sentences, and then you have people rate what they think about it. And what's alarming is that a lot of people, they assign higher inside truth values to these incoherent statements than to real statements. So a sentence like a young kid needs a lot of care is rated lower than a sentence like there is no such thing as truth. It's
rated lower of what? What scale? What are we rating?
In terms of depth of insight. Okay. A paradox, like saying there is no such thing as truth, which refutes itself. Like, is this true? If you say this is true, then there is a truth, right? But it's seen as deep insight. It confuses, there's this feeling of confusion that you get because it's non-logical.
Oh, yeah, okay.
It's taken as enlightenment. It's seen as, whoa, that's deep. Whereas,
we're all so susceptible to that, though. Yeah.
So, in fact, if you look at these studies, scientists tend to be more susceptible, often, than regular people to that problem. That is what motivates my push for formalism. Where I'm like, I think that I'm susceptible to that. So that's why I create an O-log and see there's a formal mistake. My logic isn't coherent, and so I think that. So back to the Sokal affair. So they published these fake papers. They were full of nonsense, and they got highly peer-reviewed, and they went in. And the alarming sign here was that a lot of people, they give up on math. They're like, I was never good at it. I had an F. I was really bad. But there's another problem in terms of how math is taught and what we teach math. That's why I think it's helpful to see calculating not as mathematics. Mathematics is the mathematical is what's actually interesting. But then a lot of people, I think they see equations in a talk and they just zoom out. It's like, I don't have to read the equation. I don't have to see whether this is really the Gaussian distribution. I just take this as rigorous, right? And so you can use this a little bit to hoodwink people even. And so that was my concern, that now consciousness science is grasping at the stars and is using pure math and these higher order concepts because we've run out of things to do, because we failed.
This is when now was presented the lemma, the Yoneda lemma. Yeah. That's what made you're like, oh no, we're taking a turn to the masking of the truth via high order math.
Yes, I was really concerned. It created a sadness in me because I thought consciousness is, it won't, in my lifetime, we won't make progress because now we're just going to be shrouding things in these abstract concepts that me as a neuroscientist, there's nothing I can do. And I was mistaken. So I read what the Yoneda lemma is, and I got really enthralled. So a lemma is a proof. It's a minor proof, which is ironic because this is a very major insight. And so it goes to the heart of category theory. And so I've given a talk about that on my YouTube channel, and a lot of mathematicians took a lot of issues with it. So I have to be very careful that I phrase things carefully.
Oh, okay.
But most of the critique was non-technical. I think that I had the talk reviewed by several mathematicians, and they all said this is fine. But I'm trying to explain things glibly, which is not the technical language of mathematics. But
sure.
So an easy way to understand the Yoneda lemma is that in set theory, we start with objects, so with elements of a set. And so number one, number two, and so on, or a red triangle and a blue square and so on. And then we can, for example, have a set of shapes. And then we can map that. Let's say you have a triangle, a gray triangle, a blue triangle, and a gray square and so on. And then we have another set of colors, blue, red, and so on. So we have a color set and we have a geometric object set. And then we can create arrows between, let's say a function, where I can say there's a red triangle, so where I draw a line from red to the triangle or vice versa. And so this is the foundation of arithmetic and a lot of what we can do. Now, category theory is doing the same in some ways, but it's putting the emphasis different. So it's saying what's more interesting is not these objects that you start out with, and then you draw these lines like functions, but what do you mean by a function? What is that arrow? That's what category theory is interested in. And what the Yoneda lemma shows is that if you take any kind of mathematical object, could be a number, could be a triangle, whatever you think an object is, and you know all the in and outgoing arrows, so you know how it relates in your axiomatic little mathematical world, how it relates to everything else.
The structure
of relations, exactly, then that object is uniquely defined. In other words, that object, there's nothing else to say about this object to identify it than all of these relations. So you can already think about that if I said, well, you started with a triangle, you could then make that the relation, go back to Euclid, what a triangle is made out of lines and how lines relate to points and so on, right? And so if you know all of these relations, the whole data, everything you can know about that object is in its relations. It's in the totality, it's called the Hom functor, the totality of these arrows that are in or outgoing. And what Tidenay Bradley muses about in her writing, so that's a proven theorem for category theory. So if you believe these axioms, you have to buy them, right? But if you believe these axioms, this result holds. And so it's also used in, you can already think in computer science, this might be quite interesting. And so the people are interested in that. But what Tidenay did is she said, this has philosophical implications. So if you think it's you as a person, what identifies you as a person, that Aristotelian way to think about this is I'm a human, I am a father, and so on. I have these properties. But the other view is that it's all relational. So I come from other mammals. I raise children. And so it's your relation to everything else that equally well defines what you are. So
it's like a concept space, right? Like
yes, it's like a giant graph of how you relate to anything else. It describes all your relations, what you ate for breakfast last night and this morning and so on. And so once you have the totality of all of these relations, how you relate to anything else, that's all the data's there. Like it uniquely defines you. There can't be something else in this graph that has the exact same relations and is you. So if you think about, who you were born to, who you're married with, at what point you had what friends or whatever, even if you would take all human relations, not even a conjoined twin would be the same because they have a different relation to you than you have to them. So if you take any...
go ahead. Is it a rigid graph, or can you do an eigenvector? Like, can you do transformations, or is it so high dimensional and so there are so many different hierarchical levels? You talk about hypergraphs, etc. Is it a rigid structure, or can we translate it? I mean, is my red the same as your red? Is kind of the same along the same lines, right?
Yeah, I can already see that I'm running into trouble with mathematicians because it's not really thought as a graph. It's a category. Okay. It looks like a graph. So you have these arrows, okay. But they're always arrows. For example, in a graph, it could just be a line, right? And so you would say, is it a directed graph? Well, it looks like it, but it's a category. So it's a different mathematical construct.
Okay, sorry.
But it looks like a graph, and I kind of think of it as a graph. So you're right. And so this is where you find some of overlap with Stephen Wolfram's thinking and with integrated information theory, that this graphical description seems to be helpful. And obviously, if you do category theory in practice, what I said about the O-logs, well, that's a graph that you end up in the end with, right? So there's clearly visually and conceptually an overlap. Now, what you just pointed out next, which is it just a graph of pairwise relations? Can I just use lines or arrows? That I find a really interesting question. So IIT's answer is no. And so once I had that epiphany that, whoa, you can have a graph where you can have a shared edge, a connection or relation with 3 or more objects, that changes everything. And so that's where I found some mathematicians that opened my eyes to that. We might have totally missed out on that. In particular, neuroscience, yes, we appreciate graphs. And there's a lot of graph theory in neuroscience. And now we actually even do that we use these higher order graphs. Most people are not aware of it. But when they do topological data analysis, they use these simplicial or simplicial complexes. Those are higher order graphs, technically speaking. And so we kind of are moving in that direction. There's a lot of work in machine learning as well. But Carlos Zapata-Caratala is a mathematician that has opened my eyes. He's wrote several great papers on that, where he shows that once you move out of pairwise worlds and you move into a world where 3 relations exist, some of them might be non-reducible. It's a true mathematical phenomenon of emergence. And so that may actually be very important. It seems to rule the world. So even though in mathematics, there's some debate whether everything can be reduced to pairwise relations. I mean, most of our math is pairwise. When we say multiplication, addition, subtraction, and so it's a pairwise operation. Now, you might think I can do 3 times 3 times 3 in my head, but really what you do is you use the associative law to do 3 times 3, and then you multiply by 3 again. So you keep it in pairwise operations, or you just memorize the result.
You memorize it, yeah.
If I say 17 times 47 times 65, you could probably do it, but you would do 2 and then another 2, right?
Right.
So it's fundamentally, these are defined axiomatically as pairwise operations. And so this seems to work for a whole lot of mathematics and physics, and so this is the famous example, the combustion engine. So in your car, if you have a combustion-based car, you need to have oxygen, you need to have a little bit of fuel, and you need to have a spark, some kind of heat or energy to come together at the exact precise time for an explosion to happen, and then you yield that energy to drive your car. You do this many, many, many times a second. Now, the interesting thing is, if you would study that pairwise, if you only use the air and you only use the fuel, you would never learn there's an explosion that could happen. If you only use the air and only use the spark, you would not learn this can lead to explosion and so on. So if you take, now I'm going to talk neuroscientifically, if you take the brain and you take all of these neural interactions and you just look at pairwise graphs, that's often, if you look at these papers, there's just lines between areas or neurons. You're missing out that if 2 neurons do something at the same time onto a third neuron, something else happens entirely. That's a Hebbian synapse. And we have nature papers that show that something happens that's totally nonlinear. It can't be reduced to its So if we take pairwise goggles and we try to understand the brain, it seems we're missing the most important part. It's also, this taps directly into the debate of AI in terms of, well, if it's the hardware that determines whether AI is conscious or not, well, a regular Turing machine is fundamentally pairwise. So time is not an operand. So yes, you have these clock cycles, but what happens within that clock cycle is irrelevant. So if you have an AND gate, you wait, is this signal coming in? They don't have to precisely coincide. So they come in within a certain period and you say both are on and I'm going to flip the transistor, right? And I can refresh and do it again. But it doesn't matter whether they come in with a delay or not. It gives you the same result, the AND gate. The Boolean logic doesn't really care about time, but your brain clearly does. Right? And so this is, I think, why there's these debates about biomorphic computers, SSN, spiky neural networks. So all of a sudden, that becomes an operand, and it seems to save energy. It seems to be more efficient. And IIT would say there might be a relation then to consciousness indeed as well. So because these higher order interactions are so built in the mathematics of IIT. And for me as a neuroscientist, all the way back to the beginning of our conversation, learning the math, which was hard because I'm really bad at math and I don't like it. I don't enjoy it at all. But learning that, wow, that's in this theory.
But don't you start to enjoy things as you get better at them, though? I mean,
no.
Because
it's horrible.
I'm sorry, I'm asking selfishly because I, like you, probably more than you, like I see equations and I think, oh, this is going to take a lot of time. And is it worth my effort, right?
Yeah.
To do so. But if I had a little glimmer of like, oh, eventually I'll enjoy this, that would help me, help my activation energy get closer to like, every year it's like, I really need to understand these sets of equations. And then next year, man, I really need to understand these sets of equations, and it goes on. But you're doing that hard work and it must be satisfying, but you're not enjoying it?
Not at all. It's horrible. Quite frankly, I think without AI, I wouldn't even be capable to. So I literally spent hours and hours to take Shannon's definition of information, right? Why is there a logarithm? And so I argue with the AI until I read, and then often 2 days later I forget again, because equations are so information dense in a way, right? The structure is so intricate, and but at the same time, what it does it shows you that no, I don't have to learn this equation. Really, what I have to understand is that there's a lot of assumptions baked in that are questionable. So why do we take that as a definition of information? And so are there different definitions of information? And yes, there are. So why don't we use them in the brain? This clearly, even Shannon said, isn't very good for understanding semantics. And so then why are we using that? And so I think this is why it's helpful to sit down and try to understand the equations. And maybe where some people say it is beautiful, where it's actually on this almost philosophical, conceptual level, it's hidden behind the ugliness of the notation. You see the mechanics all of a sudden. It's like the Flammarion engraving where this guy is kneeling in the world and he's putting away the curtain of the sky, and underneath, behind the sky, where the universe should be, he just sees these wheels and rotating machines and stars, and people now painted in psychedelic colors. That's more what it feels like to me, that behind it all you see the mathematical, and that's where the beauty comes in, where you see, well, if everything is relational, of course, your consciousness should be related to the brain. Of course, that should be a mathematically describable relation, and so on, where it all clicks into place all of a sudden, that yes, it makes sense that physics is fundamentally just math, and increasingly so, that because we're describing the structure of the world. And again, you can then have a philosophical debate whether that's all or whether that's what's epistemically accessible to us. And I think that's actually the minimum debate.
This goes back to, is the mathematical what's real, and everything that we perceive as physical, everything that we perceive as real is just the messiness that is somehow adhering to the tracks of the mathematical foundations of the universe?
Yeah, so I'm torn on that, and I find this one of the most intriguing questions now that I'm as far as I am, and I'm so excited that more and more people are coming on board. It mirrors a debate that Russell had, where he said, look, he understood, in science we only find relations. Like when you say the electron, the only thing that you find is what happens to it if I do something to it, or what it does to other things. And then even deeper, like, what do you mean by causality? And so it opens another whole can of worms. It's relevant for IT, that do we have a mathematics of that? And a lot of people are now thinking in terms of that doesn't seem complete. Like, it's very powerful, the math that we have for causality now, but there are issues. And so that taps into free will and so on. And so, but the deeper question, as you said, is there something intrinsic beyond extrinsic relations? I think that I'm open to both. My intuition is there's something intrinsic to my consciousness. There's clearly a first-person perspective. And what gives me pause is that now we're back to metaphors and language. And so you pointed out before the role of intuition. And so my concern is, as a psychologist, intuition, clearly lots of work shows, is based on my experience. So your intuition changes as you experience new things. And so if you test intuition down to the core, there may be a genetic component, but that's just the experience of your ancestry. And so it's basically, it allows you to deal with the world by intuition. And so my concern is, I have no intuition for the third-person perspective. I've never seen it. I can't even imagine it. What do you mean by even perspective? Like, because anything I imagine as perspective, when some people say they got perspective, well, it'd still be 180 degrees. I can't even imagine what a squirrel sees 360 degrees, right? So I'm obsessed with people that have near-death experiences, psychedelic experiences. I'm like, did you see 360 degrees? Because that should be even then it's not a third-person perspective, right? Because as Thomas Nagel said, it's a view from nowhere. It would still be centered where you're physically at. So, so what that means is I've never experienced it. I have no intuition. And so I think a lot of this debate about what do you mean everything is structure is that, yes, my direct experience is first person, and so yours as well. We only just have a first person experience. I'm a Cartesian, right? So I believe that that's all you got. You're in Plato's cave and you're seeing the shadows. Your brain constructs this first person experience and you're stuck with it. The rest is assumption. Do you really know there's radioactivity? Have you ever seen it? What do you really know about causality, right? And so I think that the problem is then when we think about the relationship of our first-person perspective, our consciousness to mathematics, it's lopsided, where we have a lot of intuition on the first-person perspective. I know what my consciousness is like, and no intuition for the third-person perspective. And so if I try to intuit about what you feel like right now, I'm probably doing very poorly, but better than that, because I kind of know what it feels like to be a human and, sit there and so on. And maybe if we take two equations and we look at them just on a third-person perspective, we have no intuition for it, but because we have none of either side, it doesn't bother us. Yeah, if I say the Pythagorean theorem, a squared is b squared, it's just abstract symbols that point at some kind of principle, but it doesn't really bother me because I don't really intuit. Maybe I have this metaphor in the head of that people draw it out, right? But if I take my consciousness and then map it onto a third-person, seemingly third-person mathematical description, it seems I have a lot of intuition here and no intuition over there, and then it doesn't seem to work. I'm like, well, I can't describe everything. But I worry that is a lot based on the fact that I intuit a lot about the first-person perspective and I can't intuit about the third. I think this is why it happens in quantum field theory, where a lot of people, when they learn, no, there are no little ping pong balls. It's excitations in a field. And you say, yeah, but what is that though? A field. They're so disappointed when they're like, it's tensors. Like it's like a 3D or 4D Excel sheet. It's just numbers at every position in space. Like, that can't be the world. It's like, yeah, but it gives us the best prediction. I think literally you couldn't have the technology you have without that, right?
Right. Well, an equation like E equals mc squared, right? So what I'm thinking of, like, all right, the end goal of IIT or any other formalized mathematical approach to consciousness is, well, let's say IIT, right, or a structural approach to understanding consciousness. So you end up with satisfying, very predictive mathematical equations, let's say a set of equations or one equation. Let's say it's simple, right? Let's say it's B equals neuron glial squared or whatever, right? That still doesn't, so E equals mc squared, we still don't really know the metaphysical, ontological nature of gravity, but we can describe it really well. It's the best way we can describe it, and we have to we have to bottom out somewhere and be satisfied with that as the explanation.
Yes.
And I think what we tend to think is that, oh God, we understand gravity because we can describe it in an equation. Well, that's not really what we're saying. We're not saying anything about the metaphysical they, whomever, experts aren't saying anything about the metaphysical basis of it necessarily, or they shouldn't be. So if we end up with that result in consciousness science, you're going to be satisfied. It's going to be beautiful.
Yes.
And it will still be an approximation because science is endless. It will be a law, but it won't necessarily say anything about the metaphysical basis of consciousness. So we don't have to step on metaphysical toes necessarily, right?
Yes. I think that's right. So I do have stronger leanings. And so my argument would be parsimony, Occam's razor. If this, so Quine has the same argument. So if this describes the world so well, and that's all I need to describe it, let's say quantum field theory, it doesn't really make sense to also assume that there's pink unicorns that magically change, that we can't see, that change particles, right? And so the argument for me, if you say, look, we have it now, let's imagine. And again, this is bad because we shouldn't have thought experiments about the future because we don't know what it's like. And people have been proven in doing that wrong and wrong again, because all we do, if you imagine, let's imagine there's a brain equation, all we're doing is we're testing conceivability, and our conceivability might be limited. Fundamentally, we're just testing our intuition now. But let's do that though for a moment, and then say, well, I still feel there should be more. If you're describing my consciousness and you can recreate on a computer screen what I'm seeing. We're getting there very quickly, right? So people can almost now, or actually to some degree, decode dream experiences. So what you see, you put in a scanner, you train with an AI, you recreate it with a generative AI. It comes very close. It certainly will happen in a lifetime. So, but that's still not the same though, right? Because I'm still looking at that from my first person perspective. Maybe I'm color weak or colorblind. It looks different and so on. So I get that you say, well, there's something intrinsic that you can't capture with these extrinsic relations. My argument would be, okay, but if you want me to adopt more in my metaphysics, my ontological worldview, there should be more than just my intuition. Like you should have some piece of data or some logical argument that forces me, compels me to accept that there's more. So I end up carefully, again, I'm a Bayesian, so I never believe I know the truth, right? So, but I end up saying, well, in terms of likelihood, have like a simplified model that all is structure seems quite on the horizon and plausible. It's not there, but like I can see that this might work. But I agree with you that I think this the danger is relativism. The danger is to say, well, science doesn't know the truth, or as I said, there is no truth. Contradict yourself, and then to say, well, anything goes, or it's just the worst statement in this realm I find is all models are wrong, but some models are useful, which is demonstrably wrong. I mean, there are some models that are one-to-one models. There's nothing wrong about them, right? So I always bring up the meter that was defined as a model. So some people came together in Paris and they took a piece of metal, they made it exactly 1 meter, and they said, that's a meter.
That's a definition. That's not a model.
That's a model. So it's mathematically, that's a model. It's a concrete representation of something abstract, right? It's a realization is what mathematicians call a model. So it's actually,
that's how they define it. That's how they define a meter. That's not a model of a meter. That's how they define a meter.
Well, okay, so so you can take a model of something, right? And so mathematicians say that's a realization, that's in model theory. And so what you're saying is I'm modeling something and you're assuming you're making shortcuts, but you know there's a one-to-one model. So, right, you could have a one-to-one model of the Isle of England. If you take it...
Well, that would be England, but then that would be England. It wouldn't be a model of England.
It would be a copy.
Yeah.
So it's a quark by quark on a different planet, right? That's a one-to-one model. It's identical, isomorphic.
Oh, okay. Well, I think that some philosophers of science would have an issue with saying that that is a model because by definition, a model abstracts something away.
Yeah, but that's not a mathematical definition. So a mathematical definition is that you and so it works actually. I think that's a confusion. I think if in science, what does because people use model as theory, but a model is a realization of the theory. So you have a conceptual theory, and then the model is usually something computational. Or mathematical formalism that is compelled by logic from your theory, and that can be tested. So it's a down arrow, not an up arrow. Okay, it's not abstracting up; it's actually concreting down.
So in the limit, I guess the famous example is if you completely replicate everything about the cat, what you have is the cat. So is one way to say it like the limit of a perfect model is a one-to-one mapping, but we just never, hardly ever get the limit. I reject your meter example, so you'll have to come up with a different example to convince me.
If you think about it though, Paul, if you think about it though, it's a model. It's a model of a meter, right? Like, so basically the meter is an abstract concept, and that's our model of a meter.
Okay, maybe we can quibble about definition versus model, but yeah, because that's how it's defined physically. But
now we define it physically as a certain distance at the speed of light is traveling a certain amount of time. That is a definition, but this is a model.
Yeah.
Like you just took a piece of it. So anyway, my point is that the problem with these kind of statements, these slogans, is that they lure you into some further thought that is not even implied, which is that all theories are wrong or something, or relative.
Yeah, you're worried about relativism. Yeah.
And so the way out, I think, is pragmatism. William James tried to say, well, some theories work better than others. You have to admit that. So not all theories are equal. Yeah. And so we all agree on that because, if I take an airplane to go somewhere, I hope that the theory of aerodynamics works better than, some ancient Greek theories about how the air works.
Sure. Yeah.
And so yes. And so I think for me, pragmatism has a problem, which is that you owe me an explanation why some theories work better than others. And so this is going to be very difficult if you don't admit that there's an absolute truth that we're getting closer and closer, more and more structurally aligned to. That there's some kind of structural overlap between my ideas and what really is. That's why it works better. So I've yet to hear a really good argument why you could have some ideas be better than others if there is no truth. That is very difficult to make that point. So then we're on the same page, right? So that, yes, even as science progresses, we're learning more and more and our models get refined. But if you look very closely, the fundamental structure always remains the same. So if you look at Newtonian physics, well, it's actually inside of quantum physics. It's inside of relativity, right? So you can make Newtonian physics a special case of these grander theories, but they don't really replace the original theory. If you look at biology, you know that the neosynthesis of using molecular biology and the inside of DNA to explain genetic evolution rather than individual evolution, pushed by Richard Dawkins, the selfish gene, and so on, that still has natural selection built in. So yeah, we're getting better and better at refining our theories, but we're never really having Kuhnian paradigm shifts. So it seems that once a theory is very good, particularly when it's formalized and mathematical, it seems that it's already very close. It's Piet Hein said, we err, but less and less and less. Like it's probably still wrong, but we have to admit it's better than many alternatives. And so then an argument could be made that at each point in time, you should admit to radical doubt that you really fundamentally don't know much. Maybe you know you exist and that's it. But some theories are better than others. And at each point in time, we're trapped in the time we live in. Those seem to be the best explanations. And then we shouldn't make superfluous assumptions. We shouldn't add something else, especially if there's no empirical or logical evidence to do so. And so for me, that makes it enthralling and enticing to toy with this idea that all is structure. And it certainly does something that my problem is with other theories of consciousness, which is it makes it non-naturalistic, where you see naturalism meaning you have one physical universe that is explained by physical laws, and then consciousness is something else entirely. And so I'm willing to accept that, but you have to make a strong argument because we kind of start out with naturalism, assuming there's one reality, it's coherent, it's causally close. So unless I can see strong counter-evidence, I want to keep going with that. And so that's the appeal of structuralism and IIT, that it takes consciousness as something that is seemingly not fit into the physical world and makes it jive. It just puts it right in there.
In the brief email exchange we had before we started recording, in the literally 2 emails, we were discussing, I sent you some topics we talk about, and you're like, okay, yeah, let's talk about that. And at some point I said, you asked me if you could ask me questions. And I said, sure, but what's going to happen? I'll tell you what's going to happen. We're going to spend, 2 hours and have barely covered, covered a ton of stuff, but barely covered any questions that we could agree on beforehand. And this is exactly what has happened.
Yes.
But there were a few things that you wanted to highlight and that I want to make sure that we also cover. And I already know, we're just going to have you back on again. I have so many questions remaining here. But okay, so you just brought it back to IIT. And you have, so we're totally switching gears here. We've been talking really deep, high-level philosophical questions. My fault, but hey, your fault too. It's your fault too.
It's interesting.
Yeah, it's super interesting. But it turns out that a soccer team is conscious. That's
to some degree.
That's not the take home. Yeah. But that would be like the highlight, right? That would be the headline, right? So let's talk a little bit because, and maybe this will segue a little bit into some of my questions about phi, the integrated information theory measure of consciousness. So you guys calculated phi based on some soccer team results. So I want you to tell me about that. And then I want to make sure we talk about your passion for this open science before we go as well. So a soccer team has some phi, has some what you guys call latent consciousness, but the phi measure is lower than any individual soccer player's phi value of consciousness. Therefore, every soccer player has an individuated consciousness. That's a summary. What did I get wrong, and what did you guys do, and why did you do this, and what should we take from it?
Yeah, you actually just nailed it perfectly. And thank you for saving me from drowning in the maelstrom of metaphysics. But I actually think these discussions are interesting because what you just said seems ludicrous. And so it's very important to do what you just said, to highlight, no, this is not just philosophy. We can actually use it and analyze data and get results. But then the results have to be look back with this metaphysical stance, because everything you said seems, if you would have told me 3 years ago, I would have said, what are you wasting your time on, Alex? So I gave a YouTube, there was a YouTube competition on explaining IT, and I found somebody in Brazil who's very good with animations, and we made some animations to explain some of the basics of IT's mathematics. And I got approached by James Watson, who's a professor at Oregon State, works in complex dynamical systems. He said, I want to use that. I want to try it in mathematics. And he said he got these data of FC Barcelona. They're tracking their players with GPS sensors at the ball as well. So you get the position of every player with millisecond precision across entire games. And they do it for all the games in the Spanish La Liga. And so we got that data, somewhat anonymized, unfortunately. It was limiting what we could do. But the idea was to treat the soccer players like neurons. And because IIT is substrate independent, it doesn't say that only your brain can be conscious. It's saying if we have something that operates exactly like your brain does, it should also be conscious. Now, the one thing we haven't talked about that I should throw in real quick is that IIT is not so much worried about the action, not so much worried about the transitions or the functions. It's very much interested in what happens in between, what we would call a states. When you said F equals MA, technically that's all at the same time, right? So F equals MA, no time passes on the E equals MC square. That's what we call a state. And so Emil Noether showed that function can only be explained with function. And so states should be states. And so there's a little throw in. So what we actually did is we had to look at states in the game. So we're not really interested in what the players are doing, but what IIT does is more interesting is we look at where the players are standing and what they could do and what they actually do. And so that is a little bit more intricate. There's a lot of computational work involved, but it gets closer at what information is and how it ties to causality. So we're looking at what a player could do and what actually happens, and that looking at the difference between these things. And so we said, okay, so if, this an old idea, if humans act like neurons, then maybe consciousness arises if it's enough neurons. And so we had to limit ourselves. That's one critique of IIT, that we cannot do this for very large neurons yet. So we're very limited to definitely less than 20 at this point, because this is a lot of math that's involved, and even the supercomputers can't quite crunch the numbers yet. So we took very small numbers, 4 players, 2 players most of the time. And then we said, look, they're active if they're not just walking around. So if they accelerate more than average, they're probably getting actively engaged in the game, or they just walk around a stand and that's inactive. So it's kind of like action potentials, that these are zeros or ones. The players are active or inactive. And then we look at this web of causal interactions, including these higher order interactions where 2 players might have an effect on a goalie that each of them alone wouldn't have. And so I suspect that based on these discussions I had about hypergraphs and these higher order relations, that we might find something in the data that otherwise, if you just look at it as pairwise, Granger causality, correlations, transfer entropy, we wouldn't see that. We didn't test for that specifically, although I've done some informal tests, and that is what seems to be the case. But what we found is that if we look at game outcome, and remember, the data was anonymized, so the best we could do is look at shots on goals. We didn't really know which goal shot succeeded and which player was which. But then we found, relatively weak, but very, very significant correlation. So in other words, if you compute the phi value of just a few players in the team, and we iterate to get an average, you can predict something about the game outcome of the performance. And then James took a second step, and so he would compute these phi values across games and then look at the top 3 teams of the La Liga at the end of the season and the rest. And so it's a bimodal distribution almost. So the top teams, they have, on average, much higher phi values than the rest of the teams. And so that is, I think what I like about it is that it shows you that despite everything philosophical that we talked about, if you're interested in sports betting, you might want to take a look at the paper. So this is the beauty about science, that at the end, this has real-world implications because you're using mathematics.
Is it implications, or is it a description? Because so is there an assumption baked in there that phi is actually doing what it is purported to do, which is measure consciousness, or based on the metrics that you're using to assess integrated information, you come up with this scalar value, but it really has nothing to do with consciousness. It is just, that's the set of axioms from which you derive all these equations and the structuralism, et cetera, and you come up with a number. And so do we really need to worry that a team is conscious, for example?
Exactly. I think that's why it's so helpful, the discussion we had beforehand. And so I have not done IT due diligence yet, but the idea is the following. Yes, you're measuring integrated information. I think most of you would agree at this point because, there's a positive outcome, and what did you do right there? But the interesting thing is, what do we mean by integration? What do we mean by information? So we're not using Shannon information here. And what integration is, we're not using a product. What do you mean by integration, right? And so there's actually a different mathematical formalism that defines these terms. And if you ask yourself, okay, so what do you mean by information? What do you mean by integration? The interesting thing that IIT does, it starts from your consciousness. This sounds crazy, but it's basically saying, what are these general universal properties that all of your conscious experiences have that are different from what you experience in the moment? That's constantly changing, but there's some things that are constant about your consciousness. And it derives these 5 axioms, or principles, if you want, a structure, that there's informativeness in consciousness, that it is integrated, one whole, not split into parts, and so on. And it builds the mathematics out of that. So when you in the end say, well, okay, you computed something, but how does it relate to consciousness? I point back to the beginning. And I say that math was inspired by my consciousness. The axioms and the math comes from what I distilled from my consciousness, the structure of my experience. There's the link right there, that we started out pie in the sky to try to do math on my consciousness, which seemed ludicrous at this point. Now we have this kind of finding, and you say, well, where's the connection? And I can trace every step along the way back to where we started with just meditating about my consciousness. So that is what's exciting. Now, still, does this mean that I can say anything about consciousness or the soccer players? Yes and no. So why do we call it latent consciousness? Well, because they're not, obviously a team is not conscious. We didn't try to show that a soccer team is conscious. But it's a test of the theory nonetheless. Because technically speaking, if we would find this really, really high phi value, and it would be, technically speaking, higher than the phi value that we assume the human brains have, IIT would have said the team is conscious, and even more, the players are unconscious. They lose their consciousness and give rise to superconsciousness. So in a way, it's not really a strong test, but the fact that we didn't find that is actually going with the theory, right? So we found a low phi value, and that's exactly what we should find. Now, the critique, of course,
it's like an expected negative result almost?
Exactly.
Would you consider it? Okay.
Yeah. Now, the critique is that we don't really know the phi value of each player in the human brain, but we can assume it's more than 6 or whatever we found for these players. So I do think that this is baby steps, that it's not a falsification of the theory, not even an attempt, but it's a demonstration of the power of coming up with a formal apparatus and linking it to consciousness by, for example, creating this axiomatic system that is grounded in consciousness.
So there are so many tweaks that you have to do, like in any analysis, right? So you use the term binarize. I mean, and we measure everything in the brain still with action potentials, which then we binarize. So it's either a spike or it's not a spike. And then so for time series like the velocity of the players, right? So you have like a continuous time signal, and then you just take the median, and ones are above, zeros are below, and so this is this huge abstraction, right? And so is that like a reliable thing to that's like a huge step. And then we're going to use that as the basis for all of the calculations, and it's necessary to binarize to do this. So there are just so many of those little steps that you think, I don't know about that, right?
Yeah, and so this is where my heart starts to beat faster as an experimentalist, right? Because if you do, let's say you got an EEG signal or a local field potential signal, and you're doing a Fourier transform. Well, the math tells you that the signal has to be stationary. So is the signal really stationary? No, it's not, right? Right. So this is actually exciting, that what we often find in science is, here could be another example that goes more deeper into philosophy of mathematics again, real numbers. You can't actually computationally decide if two real numbers are the same. We got infinite decimals. How would you know? But so what we do is we approximate, right? So we actually truncate the real numbers and turn them into fractionals, and then we treat them the same. And the crazy thing is it works. So I do not have to know pi to infinite decimals in order to build a dome. So nature isn't infinite. It's actually finite, it seems, had a starting point. We don't know if there's an end point. Quantum physics tells us that we can't really say anything coherent about a certain smaller piece of time and space. It seems discrete. And so then approximation makes a lot of sense. And so the question then as an experimentalist is how much can I violate the theory? How much can I truncate and approximate? And it still works. And if it still works, it makes the theory even more powerful. So the theory uses real numbers, and no human person has ever measured a real number. It's possible. We don't have this time and space to write down a real number, but it still works if we approximate. And so that actually, in a way, it lends even more credence to the theory. And the other thing I find interesting about it, that IIT now does, and other theories of consciousness I don't quite see to this point, is that you can now play with that. You can say, well, what if I violate this principle? Or what if I don't binarize, right? Does it still work if I don't binarize? Or what if I don't like this axiom? Like with Euclid, the fifth axiom of IIT, the exclusion axiom, is under heavy debate. When we dropped Euclid's axiom, we found non-Euclidean geometry, and lo and behold, we can make relativity work. Space-time might be curved. Now, we can do the same in IIT. We can drop the exclusion axiom and see what happens. And we maybe find a non-IITian kind of consciousness theory. But the benefit is that we'll still strictly sticking to the formal. We're not just using words and saying, well, maybe it is, this area, if it comes on or it merges to this area, we're wrong about these areas. We're much more precise in terms of, but we still have to use these other equations though, or we have to modify these equations and see what comes out of this now. And so I think that's what's exciting about when science reaches this step of maturation behind conceptualization to being more formal, that it allows you to play on a different level.
So I used to do monkey neurophysiology, and the great thing about monkey brains I have found out and human brains is that our neurons really spike a lot. So you can have a really nice temporal resolution in terms of counting the spikes over time. And you get what's called a spike density function where you can see the rate of the spiking over time. I found out mouse brains do not spike nearly as quickly. So what we end up doing is collecting the spikes and counting them in larger bins, right, to make our histograms.
Right.
And so we're kind of coarse graining the temporal scale here. And thinking about binarizing and calculating phi, is it possible? I'm wondering about the limits of like the coarse graining. Can you coarse grain and use coarse grained measures to calculate phi? I'm also thinking in terms of how being scale free is a property ubiquitous in living systems, right? And I'm wondering if you should see that kind of fractal structure such that it shouldn't matter necessarily what sort of temporal resolution or binarization kinds of procedures that you might use. Should you see the same sort of phi result, whether you're coarse graining or not? I'm sorry, that was a lot of information and question.
No, that was a really interesting thought. I've never thought about that. That's a really interesting point. And again, the cool thing is we can try, right? Yeah, so IIT is talking about coarse graining. And so it goes with what I said before, that the mathematical is the least arbitrary. So you shouldn't be arbitrarily binning your spikes. We all do, but like why, right? And so what IIT is saying, you should iterate through all the graining, and then you should find where the maximum is located, and that is the resolution you look for, both in time and space. So IIT is not assuming that spikes are what supports consciousness. That's why I said before, I'm not saying neural action, I'm saying neural mechanism. So IIT is saying, actually, the spikes itself are totally irrelevant. If you take all of these neurons and you separate their axons and they all live in a petri dish and they would fire the exact same sequence, there would be no consciousness. Well, no, right? So it's the connectivity that is very important as well. So you have to look at the pattern of activation and inactivation. Also, doing nothing is causally as relevant as doing something. It's not intuitive, but if I gift you the most nice thing in the world and you don't say thank you, it has a causal effect on me. So not doing something that is expected. So if there is a counterfactual that you could do something, that actually lends it causal power. So I need to know what is active, what is inactive, and then I need to know what can affect what. So I have to create this possibility space of causal interactions. Then I look what happens, and then I can, in a way, compute the difference. But what do I mean? What happens next, right? So, okay, you take, a nanosecond, picosecond, millisecond, and so on. Now, when it comes to consciousness, we don't have to do this crazy look. We know a picosecond or nanosecond is not we know consciousness happens on the order of milliseconds. And so we can constrain our search space. But yes, is it neurons? Is it columns? There too, we have a notion it can't be entire areas. It's not the entire brain. But yeah, maybe neurons are not enough. Synapses is probably not enough. Maybe neurons, maybe columns. So we can constrain our search space. We can then do these computations and we can find the maximum and say that is our coarse graining. Now, your idea about fractality and scale freeness, I have to read. You're going to keep me up tonight. That is really interesting. I agree with you. That would be an amazing signature.
I did it. Yeah. That'd be cool, though. Yeah, let me know if you think more about that.
So we're working on. So last thing really quick. So we're working on the tiny microscopic worm C. elegans that lives in the soil that people have done a lot of genetics with. It has gotten more interesting in neuroscience. 300 exactly, and so that seems more feasible for IIT then. And the interesting thing is they don't spike. So these neurons don't spike. It's actually an analog computer. So we're running into some of these questions, and so I'm just limited by time. But I'm burning to try out some of that.
Oh, that's cool. Okay, so in any case, so my son has a basketball game this Saturday. If they're down at halftime, I'm not his coach, but I'll ask to give a halftime speech. And I'll say something like, all right, boys, let's get out there and increase our phi value.
Exactly,
right?
Exactly.
And then I'll just walk away. And hopefully they'll intuit what I mean.
High integration.
That's the way.
High integration.
Yeah, like the winner. So anyway, just to bring it full circle on the study that you did with the soccer players. So you looked at distributions of phi values and wins, losses, et cetera. And you find that you're more likely to win the game if your team has a higher phi value, essentially. Has a higher amount of latent consciousness is another way to say that.
Yeah.
Okay, so I want to make sure that we talk about this before. And then, so after we talk about open science, are you good to hang on just for a few more minutes after that?
Yep. Yep.
Okay, because there'll be a little extra time, and we'll kind of go through some rapid things. So,
Yep.
You've been, like many people who are, you are very excited about this turn in neuroscience towards open science that's happened over the past few years as large institutes like the Allen Institute. There's the International Brain Laboratory. I just talked with Tatiana Engel that she's a part of, and I was like a board member of, and everyone is shouting that now neuroscience is going to be a lot like physics has been in the past, and that is a great thing. So what is it about this open science that has you excited?
Exactly, you just nailed it. So I think that I've been in touch with both the Allen Institute a lot and also IBL. I'm actually trying to create a bridge. I haven't quite succeeded yet, but these are two vast projects where people come together, and I think that the track record has been really encouraging, if not surprising, and
track
highly
record
successful.
Via publication metric,
yes,
or track record via that's different. Publication metric to me is correlated with, but not necessarily a perfect
True.
indicator of productivity. But,
that's fair.
Okay.
Yeah, I agree with that. Yeah. So I think that's why it's not bad we spend a lot of time talking about more than just about science. I think that there's two things that I see. I think I learn about the history of physics, and so there have been crises in funding in physics, and I think a lot of this, what we're talking about, is driven by two things. One is that the lower hanging fruit are gone. So there's a lot that when we started neuroscience and fMRI was a new thing, I remember when it was, there were things you could do that now wouldn't raise an eyebrow. And similar, there were, once microelectrodes came around, we could step through entire areas, and there was a career built by saying, that's my area, and I'm going to study that for the next couple of decades. And so that's over. And so you see that then what that means is that more effort is taken, especially for high impact publications. And again, it's an interesting debate whether that's actual progress. But there's also more and more authors involved. And I think the reason it works is because of Google Scholar and other citation tools that are saying, okay, so the old days, and so sometimes it's still unfairly the case, like we count your first author papers or your last author papers. So it's very important that you're last, or very important that you're first. And that becomes a problem if 12 people are on a paper.
Yeah.
And so I think the new way of saying, doesn't care where you're on the paper, you get, when the paper gets cited, that counts for your age index, that counts for your citations. That has broken it down. And so now it's okay to join big teams and get these big papers. Again, the physicists have led the way. And the other one is funding. And so as funding dwindles, and so I invite everybody to go and do their own research. So I found out that it's basically a geometric or maybe even exponential decay since the 60s. So if you look at inflation corrected as a percent of GDP funding in research and development, R&D, in the United States, it's been a steady decline. There's been very little blips in between, and it's a trend that we'll have to deal with. And so one idea then is, again, what physicists have done, because their experiments are getting more and more expensive, big satellites, big telescopes, particle accelerators, is to bundle up and say, we're going to all join forces. We built this expensive machine, and then all of us can use it, and we're going to share that and make progress. We can't have a particle accelerator for every university in the United States. And so I think that was the vision of Christoph Koch with the Allen Institute and the OpenScope project. And there's a lot of, for me, as somebody who was trained in the old model, the old paradigm, I was not sure this would work. I saw a lot of objections. Yeah, what about this? What about that? And I think the nice thing was to just do it and then see if it works. And so we were lucky enough that we were one of the first teams of the OpenScope project that won the competition. It was double-blinded and so on. And so then this nice thing was they collect the data, we do the analysis, and so far it looks pretty good. So things are going pretty well. And so now the next round of the OpenScope, and if you allow me to advertise a little bit and make everybody aware, because I stayed in touch. So that's completely open. So what's happening there is that review paper that I talked about is now setting the grounds for experiments are being run at the Allen Institute. And the data is published within a week. So as soon as they pre-process, they publish it. It's all on GitHub. And so what should you do? How can you profit from that? How can you become an author on maybe one of these big papers? Well, you can just join and write analysis code. And so the way it's working is that, we write the code, we publish it, and then share it. Somebody else is just built on that. We have weekly meetings over Zoom. And those get posted literally the day after on YouTube. So you can follow up. There's an entire website where you can see everything that has been done so far and where you can just jump on. There's even a discussion board that gives you starting points. Anybody can join. No PhD required, nothing academically. Any person in the world with internet access can join. And what sets the limit is, can you really, write code and contribute in the discussion and the experiments? And of course, the data is amazing. So it's what the Allen Institute can do, what other people can't do. Part of this project is, of course, two-photon imaging. Part of it is doing the exact same experiment with 6 neuropixels electrodes. And there's even an experiment where single neurons are imaged, hundreds of synapses at the same time near the soma and the dendritic tree, and you can get pretty much single glutamate vesicles. So you can see the output of the neuron in terms of calcium signals. So you can do single cell computations. So that now with this high speed two-photon techniques can be done, and you get the data for free. It's literally just sitting there as we speak and waiting to be analyzed. So the publication track record so far has been extremely positive, and my experience in these interactions, I'm like, that's chaos, it can't work. It's working out extremely well. There's steady progress. As you work on something, you push your code to GitHub, share it with other people. In the morning, you wake up and somebody else, a different part of the world, might have worked on it and done some progress. It couldn't be any smoother and faster. And so that is where I see a lot of the future of neuroscience going.
It couldn't be any smoother and faster once you learn how to interact with the API and join up and get the data, et cetera. Like, I was talking with Tatiana about this also, like, what is the learning curve in terms of how painful is it to just get up and running, essentially?
I would say nil, because for example, I said I'm very bad at math. I'm also very bad at coding, but thanks for vibe coding, right? So basically, the people publish Jupyter notebooks. I use Google Colab, so I don't have to install Python. None of that. That used to be painful in the past. So I open a Colab sheet, I put the code in, and I ask ChatGPT or Copilot to explain the code, and then I tell it what I want to fix. Now, this having said, I do know enough coding. Obviously, I've done a lot of MATLAB code writing, and so in the old days, I'm trying not to be too extreme. I can read the code,
right. So
it's just like the French I learned. I can understand a lot of French. I can't really speak it anymore, so I can read the code and I can catch mistakes, and I can see, this could be shorter, and so that is, I think, still needed. You can't just vibe code and trust it, but it's all open source as well. So other people will look at your code, and the code gets reviewed as it gets used. Lots of sanity checks built in. And so, no, I think that even if you know very little about coding and nothing about the data structure, you can use the code that's already on there that says, it loads this neuroscience without neurodata without border data, and here it is for you in a Google Colab format, and you can do it. A Google Colab sheet, for those that don't know, is literally a website where you click buttons and it runs the code and it plots the figures, and you can expand on it, you can edit it. So luckily, this all happens at the same time. That's, I think, why there's this rush of energy for trying these new ways of doing neuroscience.
I have a personal hang up, and it's like a knee-jerk reaction to like these really super large institutions, and maybe you can help me get over it. I know it's irrational, but I always root for the underdog in sporting events. And there's, David versus Goliath kind of thing. And Allen Institute, International Brain Laboratory, they're coming out with these 1,000-author publications in glossy journals left and right. And I can't help but see Goliath like in that. And it's almost like I want to root for the small laboratory doing, their own sort of thing. I know it's a fundamentally different thing because in this case, Goliath isn't like saying, well, we have all the data. And you can't have it. They're saying, here, please, everybody. And then there are pains taken to make sure that it's accessible and with tutorials, et cetera. And that's like, the biggest issue with these large outfits. And yet there's still part of me that sees it like, well, if you don't join, you're not part of the team. You're not part of you can't advance. You won't get in high tier journals. So you must join. And it's almost like a forced takeover of the academic industry publication rat race cycle. Is there any merit to that, to my scared knee-jerk anti-dominance reaction there?
I share it. So yeah, I think that, obviously I didn't grow up in the United States, and the reason I came here was that was the unique funding model of the United States. Small PIs, R01s, and so on. The problem is that it's not working anymore. And so it's working for some, but it's increasingly hard to get funding. The rates, we don't even know what the rates are anymore. They now publish the success rates. I only know that I score pretty well, and I seem to be far off. And so then the question is, what else can I do, right? And so the other one is that I think that my experience has been, the problem is not so much an institution. The problem is how democratic versus top-down it is. And so the problem is less institutionalism than authoritarianism. And so the experience for me has been that it can be difficult for a single lab to gain even the intellectual independence that seemed to be suggested. And there's a certain, practicality baked into that in terms of that, you need this lab space, we need to pay for it, there has to be a certain money coming in and so on. That then also forces you to not just do research in the blue, but listen to other people, what can be funded and what they think can be funded and so on. Now, so the way that I see that at the Yale Institute, my experience has been is that there's very little top-down, which is great. And I think people like Jerome DeCock that are running the program, I think they deserve a lot of credit to try to make it as democratic as possible. Now, there's always a little bit of hierarchical structure built in, and it's necessary because of the legal framework, right? So there's certain things we have to be careful about in terms of, well, how do we deal with authorship? How do we deal with copyright? That where it's good if you have, a general counsel nearby that can craft some legal text and so on. But the important thing for me is like, if I think back in Greek times, when we think about the birth of democracy, flawed as it was back then, the agora was the important thing, the marketplace where everybody can meet. And so that can be a pretty big agora, but you need an agora. You need a place where you can meet. It's going to be very difficult, if not impossible, for some of us to work together on big neuroscience or consciousness projects if we don't have infrastructure or a place to meet. And so that's where I can see that institutions can actually be really helpful as long as they are hands-off as much as possible. And so I think that I don't have experience with the IBL, but like at the Yale Institute OpenScope so far, that has worked really well. That again, it's just us meeting over Zoom. There is, of course, structure in terms of what we would talk about today and trying to keep things on time, but everybody has a voice. It's not like somebody raises their hand, they wouldn't be getting called on. And everybody can post on the forum. And as I said, I don't think you need an academic email address. And so that's where I thought before, does this work, does this not work? And to my surprise, this looseness and almost anarchical system really seems like it has really fostered my belief in democracy. It really seems to work. Awesome. If you get many people in the room, you get the best outcome.
Okay. Because current government does not make me feel better about democracy. And that's what I worry, so in like the Senate or something, you got to like scratch bills back and make sure Tanya's happy to get just your like little part of the bill passed. And that's sort of, I see that like, oh, that's the danger as a macrocosm. Okay. Anyway, I made a good case for it. One of the things, so you pointed me to, and I will point to, in the show notes, I'll point people to your YouTube channel, and we might be on your YouTube channel right now. And the papers that we discussed, and also a textbook, if you would like me to anyway, unless you don't want me to. So the textbook that you're writing, I actually read it really quickly because it's still in early stages, even though I'm sure you've taken a lot of time on it, because it's fundamentally a different style of textbooks where you're like, oh, you really go through the philosophical underpinnings of why what you're going to say is important, and you have to like align all those things. So much of what you mentioned today is in one form or another, like described in this textbook, in the works that so people can go to that and essentially watch you write the textbook as you write it. It's a very different kind of textbook, and I really enjoyed it so far. Some of the chapters are still blank, and I was kind of happy because it made me be able to read it faster in preparation. But I'm looking forward to seeing how that comes out as well. Alex, thank you for going over with me, and I knew it would be fun. It's been a lot of fun. So thanks.
Likewise. Thank you so much. Appreciate it.
Brain Inspired is powered by The Transmitter, an online publication that aims to deliver useful information, insights, and tools to build bridges across neuroscience and advance research. Visit thetransmitter.org to explore the latest neuroscience news and perspectives written by journalists and scientists. If you value Brain Inspired, support it through Patreon to access full-length episodes, join our Discord community, and even influence who I invite to the podcast. Go to braininspired.co to learn more. The music you hear is a little slow, jazzy blues performed by my friend, Kyle Donovan. Thank you for your support. See you next time.